heating and cooling curves. If you start with a piece of ice at negative 21.7 degrees Celsius and put it in a calorimeter that contains 91.3 grams of water at 23.4 degrees Celsius, the entire mixture has a final temperature of 11.8 degrees Celsius when it comes to thermal equilibrium. Determine the mass of the ice that was added to the water. Hence, sketch a cooling curve of water and determine what actually is happening. So I always like to draw it out because it helps me figure out what's occurring. So I know I start, where are we? There we go. So I start all the way at, negative 21.7 degrees Celsius. That's the piece of ice. So the piece of ice, this little ice cube right here, is really, really cold. It's at negative 21.7 degrees Celsius. And then I put that piece of ice in a calorimeter. And the calorimeter itself has a mass of water. And it has a temperature of 23.4 degrees Celsius. Now, when the ice then melts, right? So I have this calorimeter up here at 23.4% with a mass of 91.3 grams of water. And this ice where I don't know the grams. Well, the ice is put into the calorimeter, but it doesn't melt. I know that at 0 degrees, once it reaches that temperature, it's going to melt. And then it is going to disperse in particles in the water until it reaches 11.8 degrees Celsius. So there's a couple things happening here. There is the ice warming up to 0 degrees Celsius so it can melt. Then there's the ice melting at 0 degrees Celsius. And then there's the ice, the heat that the ice needed to dissolve in the water. And then there's one more, and then there's the heat released by the water, cooling to thermal equilibrium temperature. So there's 4 things happening here. Your ice is all the endothermic process because it's all absorbing the heat, and the water is the exothermic process. So I have my ice warming up, which will be MC delta T. I don't know my M. My specific heat of ice is 2.01 joules per gram degrees Celsius. And then my delta T. So I started at negative 21.7 and I went up to 0. So my final is 0. So it's 0 minus negative 21.7 degrees Celsius. Now I can do all that math up to the mass, and that gives me 44.051 M. I can just leave the variable. So then I have the melting of ice heat, which will be the mass times the heat of fusion. Sometimes it's moles times heat of fusion. Here, if you see the heat of fusion is given joules per grams, since I'm looking for mass, I'm going to leave it as M times 333 joules per gram. Then I isolate it to stay consistent, which will be 333 joules over M. And I forgot my joule unit here. And it's not over M, it's joules M, excuse me. Great. Then I have the ice dissolution in the water, the heat needed for those particles, once melted, to dissolve in the water. And that'll be MC delta T. I don't know my M. I'm now in the water, so I use a specific heat of the water. And I use my thermal equilibrium temperature because I'm trying to figure out how much heat was needed from 0 to go to 11.8. So sometimes it gets confusing of why am I not using the mass of the water? And it's because of this. So you have to think, all right, I have this ice at negative 21.7 degrees Celsius. In order for this ice to melt, it needs heat. So it's warming up to get to 0. Perfect. So you figured out this is the amount of heat needed to get to 0. Well, then at 0, it's not just going to stand there. It's going to start melting. So it begins to melt. Perfect. Figured out the heat that needed when it melted. But you ain't done yet because you're not at 11.8 degrees Celsius. When you are melting, you are at a constant temperature, You are just melting, or if it's vaporization, you're vaporizing, etc. So you know that when the water and the ice met and the ice dissolved into the water, eventually they reached a temperature together at 11.8 degrees Celsius. So you have to take that into account. You have to think of how much energy it took for the water to warm up to 11.8. So that's that third part of the endothermic process. So then you have the mass of the ice that you don't know, the specific heat, and you have 11.8 degrees Celsius minus 0 degrees Celsius. Now, that all comes out to, 49.3 M. Oopsies. Joules M. Alrighty, then I have my water releasing. So how much energy was it released from the water to reach from 23.4 degrees Celsius to 11? Now you're going down. So that will be the mass of the water, 91.3 grams, times the specific heat of the water, times the change in temperature from 23.4 to 11.8. Now 11.8 is your final, 11.8 degrees Celsius minus 23.4 degrees Celsius. That gives you negative 4,426.95 joules. So you know that Q endo is equal to negative Q exo. So you plug everything in. We have 49.3 M plus 333. I keep forgetting my joules. Hold on here. Joules M plus 333 joules M plus 44.05 joules M is equal to negative. You keep that negative sign because that's part of the equation. Negative, and then you plug your exothermic heat in, negative 4,426.95 joules. And then you just solve for the mass. Mass of the ice is equal to 10.39 grams. We wanted around 3 sig figs, so I would say 10.4 grams of ice. So it's essentially doing the equations that we've already learned a bunch of different times, just figuring out what's happening. So this is always a tricky part, and usually even many different people, I do this all the time, is miss one of the steps. Because you think, all right, well, the ice is in the water. It makes perfect sense that the ice has to go. I'm going to erase some of this to make it cleaner. It makes perfect sense that I know that the ice cube starts at negative 21.7 degrees Celsius and has to go to 0 degrees Celsius. I understand that. That's going to be Q is equal to MC delta T. Perfect. Then I also get, all right, well, the ice cube has to melt. It has to go from solid to a liquid. And I know that I can get that from Q is equal to the mass or the moles times the heat of the fusion. And then most people think, okay, now I'm just in the water, so now the water matters. However, the water itself all the way started at 23.4 degrees Celsius. That was your cup of water. But they both together reached a temperature of 11.8 degrees Celsius. So if you draw it yourself out like this, you can see, well, I have this part here. I have the melting, my 2. And then I have the fact that the water still needed to warm up here to disperse to reach 11.8. Once it melted, it was still at 0 degrees Celsius. So then I have to calculate the amount of heat needed for the water molecules for the ice molecules that melted to disperse into the water and reach 11.8 degrees Celsius. And then as the ice is doing that, the water is cooling down to 11.8 as well. So there's those 4 things that are happening. So it's just really, if it helps you, which it helps me, to draw out a picture and think of all of the different steps, because it's not as simple as the ice cube just melted, right? It needs to warm up. Great. Then it melts. And when it's melting, it's only at 0 degrees Celsius. So after that, it still needs to reach up to that next temperature with the water. And then the water itself is then releasing heat as well.